Alright, okay, so our first topic in vector calculus is parametric curves. Okay, so before we get into parametric curves, definition of a parametric curve, let's just review a curve that we get from the graph of a function, right? So this is standard, very standard material that you would have seen back even in, say, like Form 4 and Form 5, right? Okay, so if I have a function, say y is equal to f of x, where f of x is specified for you, right? So a nice easy example is y is equal to f of x, where your f of x over here is just simply x squared, right? Okay, so if I have y is equal to x squared, which is just this over here, this y is equal to your function x squared, but you all probably just familiar with this y is equal to x squared, and you know that you can graph this, right? Okay, so you just want to recall how we're going to graph this over here, y is equal to x squared, right? And essentially you do it if you're not using a computer system, right, and you're doing it by hand, right, there's two basic ways to do it, right? If you really never really saw it before, right, what you would do is you would first you would plot points, and then you would connect graph and see what it looks like, right? Okay, so for example, as in over here, alright, so here I have f of x is equal to x squared, and what I did over here was, right, so I specified okay, yes, the graph was here already, right? But if, say, you forget the fact that you actually had this curve over here, this parabola before, and you wanted to graph this from scratch, right? What you would do is you'd plot points, right? Okay, so you have that. You have that y is equal to x squared, right? So the f of x is equal to x squared, right? So what you have is you set up a table, right? You set up a table where this you have your x on this side, and then you have your f of x being equal to x squared. Okay, right. So for example, when x is equal to 0, you're gonna get when x is equal to 0, you're gonna get 0 squared over here, which is 0, right? So when x is equal to 0, your corresponding y value is equal to 0, and you plot that point 0, 0, and you'll get that point over there, right? Okay, so likewise, when x is equal to 1 and you put x is equal to 1 over here, you're going to get 1 squared, which will give you this value 1 over here, which gives you 1, 1, right? Okay, similarly, if you have x is equal to 2, right, and you put x is equal to 2 into this, you're going to get y value of 2 squared, which is 4, so you get this 2, 4, which is this point over here. And you keep going like that, right? And if you draw enough points like that, right, even with this small amount of points, you get an idea of the shape of the graph, right? So by simply plotting points, right, you can get the graph, right? And a computer, uh, what you can do is you can actually specify like a large amount of points, and it will build out the shape of the graph for you. Right, so here's a somewhat better graphic where you just actually seeing the points over here, right? The curve, I took off the curve, you can take it off with clicking this off, right? And here you see in the points over here, right? And just by plotting the points over here, you're getting an idea of the shape of the curve. Now, if I change the amount of x values that I plot, I should get, say, a smoother set of points over here, so you'll actually see the curve a little better, right? Okay, so I'm changing the step size. Okay, now you see, and I'm just working between the range -2 and 2, right? You see, and with more points, right, you get a better shape, right? And if you drop the step size down some more, right, basically you're gonna really essentially just get the graph over here, right? So one way of plotting graphs of a curve to determine the graph, so okay, to determine the curve uh, that is associated to the graph of a function, right, is simply to just plot the points, right? So in this case, what you're plotting is xy, right? Okay, and the x is, you're free to choose what the x is. So the x is what's called an independent value. Right? Okay, so x is the independent variable over here, right? Okay, so you're free to choose whatever x value you want over here. And then once you choose the x, that feeds into your function and determines the y value, and the y value that is determined is based on the type of function you have, right? Remember, this f of x is x squared, right? Right. So this is one way to determine uh, a curve, right? You can do it by simply just plotting appropriate points, right? And you choose in values that go into your independent variable over here, right? Right. Okay. Okay, right. So you can plot the points, right? But typically at this level, and so this is not how we're going to do it, right? Plotting the points is not bad, and if you really have no idea what's going on in terms of what the graph is going to look like or what your curve is going to look like, then you can plot a couple of points to help yourself, right? But usually, what you do is you given say uh, a specification, right? Whether it's y is equal to f of x, or when we get to say parametric curves over here, x is a function of t, or y is a function of t. So once you given this sort of information over here, what you want to do is you want to really just do it by recognition, right? So essentially you're saying, well, okay, did I ever see this before, right? Right. So for example, y is equal to say x plus 1, right? I mean, you saw that before, right? You know that this is going to be a straight line, right? You may not know exactly what the straight line is going to be, but what you're doing is you're not really going to plot points, right? What you're going to do is how you're going to work this out is you're going to look for intercept, right? And you see that the intercept over here is 1, right? And you see this, so that's the 1 over here, right? And then the slope of this is equal to 1 over here, so that gives you an idea of you have positive slope. That's not the best way to do it. The best way to do this is, well, with the intercept, and then you'd need a second point, right? So again, probably you have to fall back to plotting points, right? But the y is equal to x plus 1, at least it gives you an idea that, well, what you're looking at is you realize that this is a straight line. Okay, and once you realize it's a straight line, then you know what to do, right? You know that all you need is just 2 points and then you can plot it, right? Right, so similarly with y is equal to x squared, with y is equal to x squared, what you're looking at is you realize, well, y is equal to x squared, you recognize the form of this. This is going to be a parabola that it's facing up, right? Because your coefficient of the x squared is positive, it's just 1. Okay, so if you have y is equal to x squared, you're really going to have a parabola facing up, right? And you're not plotting points over here, right? You're doing this by recognition. You're seeing something y is equal to x squared, you expect it to be a parabola facing up, right? Okay, even if, for example, that you have y is equal to, say, x squared plus x minus, right? The fact that, right, if you have this over here, y is equal to x squared plus x minus 2, you may not know exactly what this is going to look like, but this x squared over here is what is the main term here, right? So y is equal to x squared minus 2. You recognize that this is a quadratic, right? And if you have a quadratic and your coefficient in front here is positive, right, it means that you're going to have a parabola that's facing up like this, right? You probably need to do some extra work and so to figure out well, where these intercepts are and so on, right? So where your parabola is located, right? And you do that by factorizing and so, right? And you know how to do that, right? The point is that if you once you have something like this, you should already know how to do it, and why you know how to do it is you just recognize the form of it, right? Okay, so one last basic example over here. So for example, if I have okay, so probably before I get to the x cube, let's just this will come in handy. If I have minus x squared on, right, then you know that, well, if I have y is equal to minus x squared, then this again is a quadratic, but the fact that I have a negative over here means that the parabola is going to be facing down like this over here, right? Okay, and that actually really just kind of controls the behavior, right? Because if I have minus x squared, say, right? This over here, this again is just a quadratic, but again the minus x squared over here is telling you that it's going to be facing down over here, right? Right. Okay, so one last example of this basic stuff, right? Right, so this, if I now see y is equal to x cubed minus x, what you should realize, because you have cubed over here, it's not going to be the same thing as a quadratic, right? So now this is a cubic over here, and you'd expect the cubic to look a certain way, right? Okay, a cubic is an odd function, right? So while the quadratic has this sort of symmetry over here, right? A cubic, what's going to happen is one side is going to go to, say, plus infinity, and the next side is going to go to negative infinity, like that, right? Okay, and probably you're going to have some kind of like inflection point or something like that in the middle, but you need to look at it a little further, right? But the point is, with the x cubed over here, you have a general idea of what the shape is, right? And that's pretty useful, right? So whenever you're looking at, you're trying to get a graph of anything like this, what you're looking for is you're looking for like a general sort of overall shape of it, right? Okay. Okay, so let's look at parametric curves now. So what we had before was this sort of curve where y is equal to f of x, right? And we saw what we did is we put values of x in, we got corresponding values of y. So what we got is xy points, and those xy points we were able to plot and able to get a graph, right? Okay, so now what we want to do is we want to consider parametric curves. And parametric curves, it's a somewhat similar sort of idea. Over here, what you are free to do is you're free to choose the x values here, right? You could choose any x value that you wanted. Okay, so in this example of y is equal to f of x, where f of x is equal to x squared, so y is equal to x squared, right? You're free to choose whatever x you want, right? And then the corresponding x over here would have an associated value of y, right? Okay, so for example, when x is equal to 0, you're going to get y is equal to 0, and you get a point here on your graph, right? Okay, so we want to do something similar here for parametric curves, right? But now what you're doing is you're free to choose whatever value of t that you want, right? So you're going to choose some value of t, right? Where the t is going to lie between some specified values a and b, right? Okay, you choose some value of t, and that would give you your x ordinate. You choose a next value of you choose the same value of t, and that would give you y ordinate, and that overall will give you a point xy, right? And then each of the values of t, right, once you do it that way, will give you different points, and that will sweep out a curve for you, right? So let's see an example using some software. Okay, all right, so I'm not going to use this example over here. I'm just going to use something similar, which is x is equal to 10 cos t and y is equal to 10 sine t. I need to use the 10 in order to get a large enough picture over here, right, in this software. Okay, so what I'm considering is we want to sketch a parametric curve, which is x is equal to 10 cos t, y is equal to 10 sine t, where the t lies between 0 and pi on 4, right? So it's the same sort of question as this over here, right? The only difference is that I have this 10 over here and this 10 over here, while I have 1 over here and 1 over here, right? And what that does is just scales everything by a factor of 10. But anyway, right? Okay, so we want to sketch this over here, right? Now, what you can do is one way to plot it is, as I said, what you're doing is you put in values of t, right? So this value of t over here, when t is equal to 0, so for example, when t is equal to 0, you're going to get x times 10 cosine 0, and cosine of 0 is 1, so you get 10 times 1, which is 10, right? And then when t is equal to 0, you're going to get 10 sine 0, which is 10 sine 0, and you're going to get 0 over here, right? So when t is equal to 0, what you get is you get the point 10, 0, right? Now I have this same, it's the same setup over here, and this same function values and so on, same functions and same values over here, right? The x is equal to 10 cos t, the y is equal to 10 sine t, the lower bound is t is equal to 0 and the upper bound is pi on 4, right? So this 0.79 is an approximation for pi on 4. If you check that out, you see you're going to get a 0.79, right? Okay, so t is equal to 0. I said what happens is when I put t is equal to 0 into this parametric curve, I'm going to get a specific point xy, right? So this little software over here, what is doing this, if you can see it there, it's saying that is t1 is equal to 0 0.1, right? Right. Okay, so when they're just saying t1, but that really just means a t value, right? Okay, so you have t is equal to 0 over here, and when you feed t is equal to 0 into this, and t is equal to 0 into this, you're gonna, as we worked out already, you're gonna get 10 times 1 over here, which is 10, and then when you put t is equal to 0 over here, you're gonna get 10 times sine of 0, which is 0, which gives you 0, right? So t is equal to 0 over here gives you 1 point over here, which is 10, 0, right? And if you choose a next value of t, okay, so for example, if you choose t is equal to pi on 4, which is, well, which will give you that endpoint over there, right? So how it works in this nice little software is that you can move the slider. Okay, so now this is t is equal to pi on 4, and when t is equal to pi on 4, what you get is you're gonna get these values over here, 7.04, and well, that's a small mistake over there because they're supposed to be the same, right? Okay, so that's 7.04, and you're gonna get a 7.04 over here, right? Okay, so when t is equal to pi on 4, you're gonna get a next point, right? And similarly for any other value, so this is, okay, so this guy was t is equal to 0, gave you the point 10, 0. T is equal to 0, gave you the point 10, 0 over here. T is equal to pi on 4, give you this point over here, right? And remember what we're sketching is we're sketching between 0 and pi on 4. So if we choose, say, something in the middle, right? Right? When we put the point 4 over here, right? T is equal to 0.4, we put it in for here and over here. What we will get is we're going to get a value for x and y, and the value that we're going to get for x and y would be this and this over here, and that actually gives me a point on the curve, right? So the different values of the independent variable t, right, gives me a value for x and a value for y, and a value for x and a value for y is actually just a x and y coordinate over here, right? And with an x and y coordinate, what you're able to do is you're able to locate a point, right? And the different values of t, what it does for you is it sweeps out a curve for you, right? So that's the idea behind a parametric curve, right? The different values of t give you different xy points, and that's done in a systematic way, right? Right. Well, it's done in a way that's specified by this function over here, the cos t and the sine t, right? All right. Okay, so that's the basic idea of what a parametric curve is, right? These values of t, you feed it in, and you're going to get corresponding points, uh, pairs of points x and y, which you can plot, which will trace out a curve for you, right? Okay, so here I use 0 and pi on 4, right? And that gave me this sort of quarter arc of a circle, right? Well, why is it lying on an arc, right? Well, basically why it's lying on an arc is because if you have x is equal to 10 cos t and y is equal to 10 sine t, and you consider x squared plus y squared, then you get this is an error over here, so this should be... Okay, so why it's an arc of a circle is if we consider, so x is equal to 10 cos t, y is equal to 10 sine t, and I have x squared plus y squared, right? That would give me 100 cos squared plus 100 sine squared, right? And I can factor out the 100, and I get cos squared plus sine squared. And you should remember from your trig identities that cos squared plus sine squared is equal to 1. So I get 100 times 1, which is 100, right? So if you look at this over here, I have x squared plus y squared, which is equal to 100. And this is the equation of a circle, right? Centered to the origin, right? Writing the 100 as 10 squared means that the radius of the circle is 10, right? Okay, so this is an equation of a circle, right? But what I have over here is um, 1/8 of a circle, right? And because I'm going between 0 and pi on 4, right? And that's the key thing over here, right? The x, this x is equal to 10 cos t and y is equal to 10 sine t, right? This over here satisfies x squared plus y squared is equal to 10 squared, right? But that doesn't mean that the parametric curve is going to be a circle, right? What it means is that the parametric curve is going to be a subset of a circle, right? So this x and y, right? Any xy over here satisfies this, right? So any xy over here, in fact, lies on a circle, right? But it doesn't go in the next direction, right? It doesn't mean that any point over here on the circle would satisfy this criteria. It will satisfy this and it will satisfy this, but it will not satisfy, not necessarily satisfy this, because this is the restriction over here, right? So this is what gives me the 1/8 of a circle, right? If I change this pi on 4, I will get different things, right? So for example, if I use 2 pi, right, what I get is I'm going to get the entire circle, right? Right. And it's the same idea for this over here. Now this is cos t sine t, but this over here now is saying that the t is lying between 0 and 2 pi, right? Okay. All right. Let's change these values again, just see if we get some idea what's going on. So let's say if we use pi. Right. Okay, so if I use pi, what happens is I'm going to start at when I put 0 in over here and 0 in over here, I'm going to get the same starting point. But when I put pi in, what's going to happen? I'm going to get 10 times cosine of pi, and cosine of pi is -1, so I'm going to get -10 here. Sine of pi is equal to 0, so I'm going to get 0 over here. So what I have is -10, 0, and -10, 0 is this point here, right? So if you slide all the way across at the end, and if I could get right to the end, which I apparently can't, you would get -10. Right, here we are. Right? So you get -10, 0, which, so when t is equal to pi, you're going to get -10, 0. So what that's saying is, in situation when you have a parametric curve from 0 but now this is no longer pi on 4, it's pi. What you will get is you'll get half of the circle, right, of radius 10, right? Let's see if we could make this, keep going with this example. Right. Okay, so what I did now is I'm going between pi on 2 and pi, right? So I'm starting at pi on 2 and I'm ending at pi, right? Okay, so when it's now pi on 2 over here and you feed pi on 2 into this, when you feed pi on 2 into this, cosine of pi on 2 is equal to 0, right? And sine of pi on 2 is equal to 1. So I'm going to get 0, 10 over here, which is this point, right? So t is equal to pi on 2 gives me the point 0, 10, right? And the point, the value t is equal to pi gives me the same minus 10, 0 that I had before, right? Okay, so going from pi on 2 to pi gives me a quarter the circle, right? And next example here is okay. So if I now use 7 pi on 4, right? What 7 pi on 4 will do? Uh, it will it will start at pi on 2. Now, the pi on 2, the interesting thing about the pi on 2 is the pi on that this t over here, right? The t is actually this starting value is angle subtended, right? Okay, so you go in over here. If you consider in clockwise, measure an angle clockwise in a standard way, go in from your x-axis, right, and rotate in. Sorry, not clockwise, but counterclockwise, and you rotate counterclockwise this way, right? Going from here to here counterclockwise is pi on 2, right? So you're starting at this point over here, right? And going from here right around up to over here, right? So you could imagine that you have a line connecting here to here, like similar to this sort of line there. And that angle going right around over there would be what I used, which was 7 pi on 4. Okay, right. Okay, and if you want a simpler example, then right, if I use 2 pi, then 2 pi will get me back to this 10, 0 over here, right? Okay, so this is, as I said, you could think of this in terms of angles. This is pi on 2, so pi on 2 is from here to here, right? That angle there is pi on 2, right? And the angle, if you go right around like this over here counterclockwise and you come back around like this, that is 2 pi, right? So that's why this arc came back to this point over here. Right, okay, so a parametric curve given in this sort of general form, x is equal to f of t, y is equal to g of t, where your parameters t lie between a and b, right? Okay, so x is equal to f of t, y is equal to g of t, where t lies between a and b, right? This can also be written in vector notation, right? And it's equivalent, right? So if you see something like this over here in vector notation, right? Uh, it just means that the x is equal to the f of t and y is equal to the g of t, right? Here the I and j are your standard unit vectors in the plane, right? Okay, so the I is your vector of length 1 line along your x-axis like this. And similarly, the j is line along the y-axis like this over here, right? This you can justify a little bit that this is actually equivalent to this. You can, right, if you use this over here, right? Right. So the r of t, right? Remember what this r of t means? It means, well, means that this is consistent of two components, x and y, and the x can vary with t and the y can vary with t, right? Okay, so r of t basically by definition is x of t, y of t, right? Okay, now if you look on this side over here on your right hand side and you work this way, right? The f of t I plus g times j, right? The I is this unit vector here. The j is this unit vector over here, right? Okay, and this function over here, how you operate over here is f of t times this vector means what you're doing is using scalar multiplication. So it's going to be f of t over here and then 0 over here. And then in this case, when you multiply over here, you're going to have 0 over here and g of t over here. And when you add these two, you're going to get this, right? So working this way, I get f of t, g of t. Working this way over here, I get x of t, y of t. And that tells me that the x of t is equal to f of t and the y of t is equal to g of t, right? That's a little bit of justification, or if you want, you could just read this. Once you see this over here, this just means x is equal to f of t and y is equal to g of t, right? Okay. Right. Okay, so now we have this aspect of smoothness. Right. Okay, so for parametric curve, we have this notion of what of smoothness here, right? Okay, so a parametric curve in plane specified in this vector form that I previously talked about, right, is said to be smooth if your component functions, in other words, if this x function over here and this y function over here, the g of t, right, if those have continuous derivatives on the interval here, a to b, right, and the check is actually not including the endpoints, it's just what's lying between, strictly between a and b. All right. Okay, so this is a somewhat sort of technical definition. You should know, have an idea. I want you to have an idea of what it means, right? The check like this over here for continuous derivatives means that you need to check for continuity, and checking for continuity is checking formally for continuity is probably a little bit beyond the scope of this course. You need to have an idea of what the continuity is, and we will talk about that a little later on. But this overall notion of smoothness, what I want to do is I want to explain using a simple example. All right, okay, so let's look at this example over here, right? So we want to sketch this parametric curve, right, which is given in vector form, right? The f of t in this case is t, and the g of t over here is mod t, right? And the values a and b over here between -5 and 5, right? Okay. Right, one thing you want to notice, okay, so first before I do this over here, let's just plot it using the software, right? Okay, so here the x function, I put it in and it's t. The x function I put in and it's t over here, right? The y function, when I put it in mod t, the software converted it to absolute value of t, which is the same thing. Okay, and then the lower bound, the a is -5 and the b is 5, right? And it plotted it for me, right? And when you plotted it for me, you got this over here, which basically is just mod x, right? This function, this is the graph of, this is graph y is equal to mod x over here, right? Okay, so what I want you to notice here is that over here, this is smooth, right? You have no sort of like kinks and so in the graph, right? The only place where you have a kink in the graph, right, is actually at this at the origin over here, which corresponds to when t is equal to 0, right? Okay, so this kink means that when you go from here to here, the derivative value switches from -1 over here to 1, right? So that your continuity of the derivative fails at that point over there. But anyway, the key thing over here is smoothness for us. If it's smooth, it means that you're not going to have any kinks. So this piece over here, all along over here up to here, that's smooth, right? It's only one point on this parametric curve where it's not smooth, and that's when t is equal to 0, which is exactly this kink over here, right? Okay, so smoothness for us means, well, okay, so not, if something is not smooth, means that it's going to have this sort of kink, which means that there's a sudden change in the derivative, okay, at the point that you're looking at. Right. Okay, so, but back to our example. The example was, so, looking further at the same example, sorry, right? So it's the same example that I'm looking at, right? So the x is equal to t, the y is equal to absolute value of t of mod t, and you go in between -5 and 5, right? Right, so the software will graph it for you, right? But how do we get an idea if we don't have the software, right? So the idea over here is that, well, remember this is in vector form. It means that x is equal to t and y is equal to mod t, right? And the idea here is that if you're not quite clear as to what this is, right? One way to graph these things, right, to graph parametric curves is to just eliminate your parameter t, right? And in this case, it's pretty easy to eliminate the parameter t because the t is actually equal to x, right? So all you need to do is just substitute x for this t over here, and you get y is equal to mod x, right? Okay, so what this says is that any point on your parametric curve lies on y is equal to mod x, right? Does not mean that any point on the graph y is equal to mod x will satisfy this entire thing, right? And the reason why it may not satisfy this entire thing is because of this extra condition over here, right? Okay, so this condition over here, what it does for me is it chops off a piece of the entire y is equal to mod x. So y is equal to mod x is going all the way from here and right over there. And the -5 to 5 will just chop it off from here to there, right? And the chop is, for example, the t is equal to 5. When I plug t is equal to 5 into t is equal to 5 into this, I'm going to get 5, 5, which is this point, 5, 5, which is this endpoint, right? So t is equal to 5 gives me one endpoint, and t is equal to -5 will give me the next endpoint. Okay, so that tells me how to chop it off, right? Okay. Right, so in this particular case, it was easy to eliminate the t over here, and you get this. And this over here, seeing that you're more familiar with graphs of functions y in terms of x, right? It'd be easier for you to probably sketch this than to sketch this, right? So the point I don't want to make here is that sometimes if you want to sketch parametric curves, one way is to eliminate the parameter t, right? And essentially that is actually exactly what we did over here, right? In our case with the cos t and the sin t, right? Because we started off with x is equal to cos t and y is equal to sin t. And what we did is right, okay, let's look at this example. See, now that I have to work in it is that x is equal to 10 cos t, y is equal to 10 sin t, right? Okay, and what we did is we considered x squared plus y squared, right? And x squared plus y squared turned out to be equal to 100, right? So just this trig identity, what it did for me is it eliminated the t, right? So I went from this expression over here to something which is x squared plus y squared, which is 100, which has no t in it, right? So I eliminated the t here, right? And the idea here is that this is, again, you should be familiar with something just purely in terms of x and y, right? So one more time, if you want to sketch a parametric curve, one way to do it, if possible, right, is to eliminate the parameter t. You may not always be able to do it, but it is one approach, right? Okay. Okay, so what we looked at so far was a parametric curve in the plane, okay? So this is, if we consider this parametric curve in the plane, and say we take t is equal to 0 and we substitute it in here and here, right? We're going to get x is equal to cosine 0, which is 1, and we're going to get y is equal to sine 0, which is 0. So we get 1, 0, the point 1, 0, which is a point in the plane, right? Okay, and each of your t values in this interval between 0 and pi on 4 is just going to give you a different point in the plane, right? So that's because you only have x and y over here. Now, if you have x as a function of t, y as a function of t, right? X is a function of t, y is a function of t, but now additionally you have z as a function of t, right? What this z is doing for you, it's now giving you height, right? So putting in some value for t over here gives you x, y, and z, gives you a point x, y, z, which would be a point living in three-dimensional space like this here, right? Okay, so in three-dimensional space, this this red over here, red direction over here, this is in the x direction. The green over here is in your y direction, and then the z over here, this blue over here would be in the z direction here. Okay, right, so you can specify a parametric curve in three-dimensional space by given each of your components here, or you could write it in vector notation, right? So notice this is the same thing that happened for a parametric curve in the plane, right? You could specify it by components like this, or you could write it in vector notation, right? So this statement over here, including the t line between a and b, is equivalent to this statement here. And we have a similar notion of smoothness, right? So your parametric curve is going to be smooth. What that means is that you have no sort of kinks in it, right? And again, it's possible to formally check if something is smooth by looking at the derivatives here and checking to see that the derivatives are continuous. Right. Okay, so let's look at a specific example, right? This parametric curve over here that's specified that the x is equal to t, the y is equal to t, and then the z is equal to 1 minus t over here, right? Right. What you want to notice over here is that this is t to the power 1, likewise this is t to the power 1, this also is t to the power 1 with a constant over there, right? So what that means is that everything over here is linear, right? Yeah, and roughly what that means is that you have no sort of like t squared or t cubed or square root of t or cosine of t, right? It's just t, right? And once you have this sort of form over here where x, y, and z are all linear functions of t, then what that means is that this over here is just going to be uh, a part of a straight line, right? If you didn't have this restriction here, if you didn't have the specification that the t is going to go between 0 and 1, right? Then what you'd in fact have is you'd have just a straight line, right? Which you saw how to do the equation of those in ENGR 1180, right? But anyway, once you have it restricted like this, what this means is that you're chopping the entire straight line, and when you chop on two ends, what you get is you get a line segment. All right, and once you realize that this is a line segment, it's easy to graph, right? All you need is the start point and the end point, right? So to graph a line segment, you just need to figure out what's the coordinate of this point over here and what's the coordinates of this point over here. Right? And that's not hard to do. T, you just put in the end points of your range here, right? So t is equal to 0 when I substitute in, gives me 0, 0, 1 minus 0, which is 1. And t is equal to 1 gives me 1, 1, 0, right? So 1, 1, 0. Okay, so t is equal to 0 gives me this point over here, and t is equal to 1 gives me this point. You just draw them on your graph of a three-dimensional graph here, right? And you plot them. This is positive x direction, this is positive y direction, this is positive z direction. Okay, you plot them, right? And then you just connect these two endpoints by a straight line. So that would be your parametric curve. Okay. All right. So let's do it over here, say in the software as well, right? So we have t, and we have 1 minus t. Go in between 0 and 1. Right. So we plot them. We have x of t is equal to t, y is equal to t, z is equal to 1 minus t. The a is 0, the b is equal to 1, and when we plot it, we get this over here, right? So we get a straight line segment, and that actually is the same as what we have, right? This obviously is a little better because you can rotate and see what's going on. And right. Okay, so you see in this point over here, it's on your z-axis. So once you're on your z-axis, the x and the y is equal to 0. And here it's intercept, the intercept is z, intercept over here is 1. So this point is 0, 0, 1. Okay, and you see in the 1 over here for the x, the 1 over here for the y. Right, so this is x is equal to 1, y is equal to 1, and this is on the xy plane over here where the z is equal to 0, so this point over here is 1, 1, 0, right, which agrees with what I have here. Right, okay, so this is one possible parametric curve in three-dimensional space, right? If I change my components over here, so for example, if I change this to cos t to sin t, and then to t, right, I'll get something different, right? Okay, right, so once if I use this x is equal to cos t, y is equal to sin t, and z is equal to t, right, well, the x is equal to cos t and the y is equal to sin t. That should actually remind you of what we had over here, right? X is equal to cos t, y is equal to sin t. Those without the z gives you something that wraps around your origin like this, right? So the x is equal to cos t and the y is equal to sin t, right? Is causing the x and the y to wind around your z-axis like this over here, right? And so it's causing the x and the y to wind around your z-axis, and what the t is doing, the t is lifting off, right? You increasing your height as you go along, right? So it's as if you had a circle over here, but the height of the circle started to increase, right? And it started to wrap around your z-axis, right? Okay, so this sort of object over here, where x is equal to cos t, y is equal to sin t, and z is equal to t, right? That is an example of a helix. Okay. Right, so here on Wikipedia you have probably a nicer diagram because the scaling is better over here, right? Okay, so you see in over here the parametric description of a helix: x is equal to cos t, y is equal to sin t, z is equal to t, right? Which is what they have here: cos t, sin t, and t, right? And in this case, they're using t going between 0 and 4 pi, right? Which is somewhat close to what I have. Right. Okay, so 4 pi is. Right. Well, actually, yeah, it's not that. 10 could be better, right? 4 pi is 12, 12.3, roughly 12.4. So I should use 12.4 here. Right. Okay, so you see that it wraps around once and then it wraps around again, right? Their axis orientation is a little different also. Right. Right. Okay. So yes. Right. So starting over here, corresponding to starting over here, and then going around and coming back around over here. So going around and coming back over here. Right. So this point over here and would be directly above. This point over here is directly above this one. Right. It's a little harder to see it over here. You're going to have a point down there, and then the point directly above would be this. So this obviously is a better picture, but it's the same thing, right? What you're doing is you're winding around your z-axis over here. Okay. So we looked at parametric curves in the plane and in three-dimensional space, right? Okay, so for example, this here is a parametric curve in the plane, which is 1/8 of a circle of radius 1, right? Okay, this here is this one also. This is a parametric curve in three-dimensional space, right? Okay, so the equation of that parametric curve is this over here, right? And when you graph it, we get this straight line segment. Okay, and this is in three-dimensional space. And we also briefly talked about parametric curve, which is x of t is cos t, y is sine t, zeta is equal to t, right? And that gives you a helix. Now this is a parametric curve in three-dimensional space. Okay, so for either parametric curve in the plane or for a parametric curve in three-dimensional space, what we want to do is we want to determine its arc length, right? All right, so well, what is the arc length, right? In the case of this over here, this parametric curve in three-dimensional space, the arc length is pretty straightforward, right? The arc length is just simply the distance from this point over here to this point over here. So you're going along a straight line like this, so it's easy to get the distance over here. Uh, this is something you would have known how to do or would know how to do from sixth form, right? Okay. However, if you have something a little more complicated like this over here, right? What you want to do is you want to get the arc length, right? Or even more complicated, say like this here, you want to get the arc length, right? Okay, so first of all, what intuitively is the arc length, right? Okay, so let's see, let's use this diagram here. Right, so if I have, say, a curve over here that's, say, well, it's not straight like this, right? The arc length is what you get when you straighten it out over here, and then you measure the straighten length. Okay. Right. So that's what we want to do here, right? Any curve, say this curve over here in three-dimensional space, if we want to get the arc length, what you're doing is you're thinking of this as inextensible string, so you can't stretch the string, right? What you could do is you could take it this end over here, this end over here, and then you can straighten it out, right? You can't increase the length, you can't stretch it, right? So it's inelastic, so like a piece of thread, right? But you can straighten it out. What you want to do is you want to measure the length of it, and that length is called arc length. Alright, so for us, how you get the arc length, it depends whether you have a curve in the plane or you have a curve in three-dimensional space. If it's a curve in the plane, then what you're going to be doing is you're going to be using this formula, right? Okay, so you have your description of you have your specification of your parametric curve, right? Your parametric curve would have x component here, which is a function of t, y component, which is a function of t, and then it's going between t values a and b, right? So for example, in the case over here of this parametric curve, the x of t is cos t, the y of t is sine t, and you go in between 0 and pi on 4, right? So the a is equal to 0 and the b is equal to pi on 4. Okay, right, so how you get the arc length from this sort of specification is you take the x here, the x of t, you differentiate it with respect to t, right? Take the y of t and you differentiate it with respect to t. You square in each of those, you add in them, and then you take in the square root of that, right? And then once you get this over here, you integrate that between these limits a and b here. And if you have a parametric curve in three-dimensional space, it's a similar formula, right? In three-dimensional space, your parametric, you have three components now: x of t, y of t, and z of t, right? So you're going to be doing something similar. You take this, differentiate with respect to t. Right, take the y of t, differentiate with respect to t, take the z of t, differentiate with respect to t. You square in each of these, add in, and then take in the square root of that. And then finally integrate in between a and b, right? Alright, where that formula comes from is, if you want, you could take a look at the active calculus textbook. And really what you're doing is you're going to approximate first of all, and then you take the limit of the approximations. Um, so this limiting procedure that I'm talking about, let's use this little example here to get an idea what's going on, right? So I have this parametric curve, which is x is equal to cos t, y is equal to sine t, and the t going between 0 and pi on 4, right? This diagram isn't isn't extremely great, right? So you go in between 0 over here, t is equal to 0, to t is equal to pi over here, right? So really you should just be seeing this piece over here, and this, if you uh, if you look at it, it's a little darker over here, right? This arc over here is not supposed to be here, right? So what you want to do is you want to get the length from here to here, right? And the integral formula is really coming from approximating, right? Okay, so what, for example, if you notice, if you by approximating, what you're doing is you're approximating your parametric curve by line segments. Okay, so here this is an approximation. These two green line segments over here are roughly the shape of this parametric curve, right? And it's not hard to get the length from here to here and the length from here to here, right? So length from here to here plus the length from here to here, right, is approximately equal to this arc length, right? Okay, so that's an approximation. It's probably not the best approximation, but it's what to start off with, right? Now, this is using two line segments. If you use, say, three line segments, what you'd get is, and then what you do is you work out the length from here to here, length from here to here, here to here, and then you add three of them, right? And that length, that total length is uh, approximating this arc length, and now it's a better approximation. If you notice, if you look at these three over here, right, they more closely fit this shape, this arc length, this arc over here, right? Okay, so that's when I use 3, right? If I use 4, right, you see that the green lines over here are approximating the arc. It's a better approximation of the arc, right? And again, if you want to get, what you could do is not hard to get add up the lengths of these four, and that would give you an approximation of the arc length. And you keep going like that, right? So if you go to say 6, right, you realize that you get in this length over here if you do it this way, right? And you add up these the lengths of the 6 line segments, right? Then you get a pretty good approximation of your arc length, right? And if you go further with this, say if you use 10, right, then it gets pretty good, right? And if you use say 20, then it's extremely good, right? Okay, and even if you use say like 100, and so basically you'll be able to calculate the arc length, right? So the getting the arc length of that is okay. So that's what's happening over here, right? This L over here, your arc length is the I is equal to 1 to n. Right. Okay, so if you looking at say these 4 line segments here, right? Uh, in this formula here, so this is in the active calculus textbook that I posted a link for, right? The n here is equal to 4, right? Your index is running from I is equal to 1 to 4 over here, right? What this square root over here is doing is this is calculating the length of each line segment from here to here, right? And you have 4 of those, and then what you do is you calculate the length from here to here, here to here, here to here, and here to here, and that gives you this uh, right hand side over here, right? In the case when n is equal to 4, right? And this right hand side, in case n is equal to 4, is approximately equal to the true arc length, which is denoted by big L in this textbook, right? Okay, so that's the idea, and so that's where the formula is coming from, and then you need to use a certain amount of calculus and so on, right? They rewrite this expression and using with a delta t, right? And then they use a definition of a derivative, right, to rewrite this as uh, a derivative over here. That's strictly speaking supposed to use probably a mean value inside over here, right? And then notice you have a limit over here, right? So the limit n going to infinity over here is the same sort of limits that I was doing here, right? So n is equal to 5 gives you a better approximation. N is equal to 7 gives you a better approximation. So notice over here what I'm doing is I'm increasing the n, right? So uh, n is equal to 10 will give you a good approximation. And when the n increases, basically, effectively, you're really just getting the actual arc length, right? Okay, so the formula that we have here, right? It really is coming from right. This sort of proof of the formula is comes from uh, an approximation, right? By using approximations. Okay, right, and they actually derive the same formula as this. It's in a slightly different form. Here they use uh, r prime of t, but r prime of t, the modulus of r prime of t, is really the same thing as what I have over here, right? They're doing it here in the active calculus textbook. They're doing it in this general case of it. Well, not general. They're doing it in the three-dimensional case over here, right? Okay, so that's where your formula comes from, right? The formula comes from by approximating the parametric curve by line segments. Anyway, what we want to do is you want to be able to use this formula, right? So let's get the arc length of this parametric curve, right? Which is cos t I sine tj, where the t goes between 0 and pi on 4, right? And this parametric curve, we looked at something very similar to that, right? And this parametric curve here, uh, the sketch of it is given on page 5 here, right? So it's this parametric curve going from 1, 0 to 1 and root 2, 1 and root 2, right? Okay, so what we want to do is we want to get the arc length over here, right? You probably know from, say, your high school maths and so on, right, that you can get the arc length of that using S is equal to R theta, right? Because what you have is the R over here is equal to 1, right? The theta measured in radians here is pi on 4, right? So the answer that I expect to get for this arc length is going to be 1 times pi on 4, which is pi on 4, right? Okay, so the S here, this arc length, that this formula that you know, S is equal to R theta, that's the same sort of arc length that we talking about, right? Okay, but this here works for a circle, right? What we want is we want an arc length formula that would work for more general cases, more complicated curves rather than simple curves, such as a circle over here. Anyway, so you want to work out the arc length of this parametric curve, and it's not really too bad, right? You're just using this formula over here. Okay, so you take the x of t is cos t, right? So what you need to do is that x of t, you need to differentiate it with respect to t. So you take the x, differentiate it with respect to t. When you differentiate cosine of t, you get minus sine t. And similarly, the y, you need to differentiate with respect to t. So you differentiate the sine t with respect to t, and you get cos t, right? You square in both of those, right? So when you square the minus sine t, you get sine squared t, and when you square the cos t, you get cos squared t, right? Okay, so I have square root of sine squared plus cos squared t, right? Now the thing about doing these arc length problems, right, involving your square root over here is that once you put in your components and you simplify like this, you pretty much would always end up with something involving a square root, right? And if you have some practice with your integrals, then you'd know that integrating things under a square root sign is not necessarily the easiest thing, right? So somehow the square root sign needs to go away, right? Okay, which means that the inside over here, you need to simplify it somehow so that the square root sign, um, you could somehow eliminate the square root sign. Okay, and in this case, it's not too bad because what you do is you use your trig identity that sine squared plus cos squared is equal to 1. So here you have square root of 1, and this is what I mean by the square root sign going away because square root of 1 is just 1, right? Okay, so all I'm doing here is integrating 1 between 0 and pi on 4. And when you integrate 1 with respect to t, you get t. Put in your limits pi on 4 and 0. So what that means is that you would have pi on 4 minus 0, which gives you pi on 4, right? Okay, and that agrees with what this formula over here, that s is equal to r theta. In this case, your radius is equal to 1, right? And the angle is pi on 4, so 1 times pi on 4 is pi on 4, which is what I got over here.